Okay, in this video we're going to talk about resistance, reactance, and impedance. The first thing to understand about them is that they are all opposition to the flow of electrons in a circuit. And perhaps the easiest one to understand is resistance in a direct current, DC current source. This is where the current flow is at a constant rate. And the resistance is the opposition to that, and the energy that's lost is oftentimes given off as heat. Okay, but we get into a vastly different world when the source is no longer direct current, but is alternating current. The operative word here is current, not voltage. But in an AC source, the voltage is also changing, can be changing, typically changes, I'll put it that way. Okay, and almost all circuits have some sort of a purely resistive element to them. They also have a capacitive element to them, and they have an inductive element. Now these can be discrete components, resistors and capacitors and inductors. But even a wire like coax, for example, it has a certain amount of DC resistance to the flow of current through it. It has capacitive reactance. It has inductive reactance, because anytime you have a wire and you pass a current through it, it sets up, I'm not drawing fields very well here, those are circles around there, but we have a magnetic field around that wire. Okay, so the opposition to flow of electrons in a circuit offered by a capacitor is reactance. Resistor still stays as resistance, and all three of these, by the way, are measured in ohms. That's the unit. But there's a difference between resistance, pure resistance, and reactance. Reactance uses the letter typically of X, and X sub C for capacitive reactance, and X sub L for inductive reactance. So where does that leave us with impedance? Well, impedance, which uses the letter Z typically, is whatever the resistive component is plus whatever the reactive component is. That's the total amount of opposition to the flow. And in an alternating current scenario, that's called impedance. So it is resistance to the opposition. And impedance becomes important. Let me do this little illustration here. I like this analogy when I'm talking about antennas and whatever. This could represent a feed line. We're talking about impedance matching. Well, first of all, let's forget about electrons for a moment. It's easier to picture water, for example, flowing through a pipe. And you can see here where we have a complete mismatch that's not even close. None of the water gets into, if this is our end result out here, none of the water is making it to the reservoir, so to speak. To get the maximum transference of water, or in the case of electron flow, the energy, we need to match these better. And so as we get closer and closer to a good match, now we're getting basically 100% of the flow from the source out to the destination. Now, in electronics, what we're talking about impedance matching, for example, one of the key examples is hooking up an antenna to our radio, because in order to do useful work, obviously We need to be able to connect it to an antenna, not only to receive, but to transmit. So we want the greatest efficiency we can from the energy coming out of the back of our radio to get to our antenna system. And we can do that by making sure that we have a good impedance match between the radio and the antenna system. However, having a good match here does not guarantee maximum efficiency of an antenna. That's all dependent on an antenna design. So don't get that confused with the efficiency of an antenna system. We just don't want any opposition to the flow. Okay, think of it this way. I could have maximum transfer of energy from the back end of my radio and going into a coat hanger and have a perfect impedance match, but a coat hanger is probably not a very efficient antenna system. Whereas if I have a 4-element beam with high gain, I've got an efficient antenna for receiving as well as radiating energy. Okay, so that's the idea with impedance matching and why that's so important. Okay. Well, we want to be able to compute what our reactance is, just like we use Ohm's law in DC circuits to find out resistance and current and voltage. We can also calculate power and so forth. We can also do the same thing with alternating current. But we have current that is alternating. This is a sine wave. Well, we'll think of it as a sine wave. It can be modulated if we're talking through it. And these, of course, would be identical on both ends. All right. But the components behave differently. Not so much the resistor, but the capacitor and the inductor, they behave differently than they would if they were in a DC circuit. First of all, current would not flow if we had a capacitor here because the capacitor looks like an open circuit. And if we put an inductor over here, the current is constant, and the coil of wire would just look like a direct short. But when we introduce the idea of frequency, now reactance becomes a very big component of what we're talking about. And we're going to look at how to calculate this in probably the next video. We'll take a look at capacitive reactance and inductive reactance. And we want to tie that together with how they're related to frequency. And I'll give you a little peek ahead. We can determine the resonant frequency because these are related. They're related by 2 pi times the square root of the inductor times the capacitor. That's in farads and henries, or the microhenries. Anyway, this will give us, I forget what the units are, we'll talk about that separately. And this will give us what the resonant frequency is in megahertz. And why do we care about resonance? Because that's where the reactance between capacitive reactance and inductive reactance, that's where they are the same. We get resonance there. And when we have resonance, we have the maximum flow of energy. So that indeed is a very important concept. All right, we'll talk about that in separate videos. Hopefully this gives you a little bit of a leg up on what resistance, reactance, and impedance is. The main takeaway here is that impedance is a total of all of it, the resistive component as well as the reactive components. Reactance is the resistance offered to the current flow of that. As frequency, for example, as frequency goes up, the reactance of the capacitor goes down. At high frequency, a capacitor just looks like a short to RF. Whereas with an inductor, because we're building up magnetic field rather in here, it's a finite amount of time it takes to build that field, and then the field has to build and collapse, and the higher frequency, the more frequent that it has to do that, the more opposition to the flow of current it offers. So as frequency goes up, so does inductive reactance, and it's just the opposite for capacitor. Okay, I think that's enough for this video. We're over time, so we'll talk more about these when we talk about the individual components. All right, see you in the next video.